Welcome to The Explainer. Today, we're diving straight into the fundamentals of robotics, and we're going to be drawing from some fantastic research material by Dr. Sudheendra S G, which was put together specifically to help teachers and educators like you get a real handle on these core concepts so you can teach them effectively.
Okay, so here's our game plan. We're going to start by figuring out what actually makes a robot a robot. Then we'll uncover the secret sauce that really makes them work. After that, we'll look at the smart controls that fine-tune their actions, see how the whole system fits together, and finally, we'll get into their real-world impact and some of the tough questions that come with it.
All right, first things first. We need a solid definition, something that cuts through all the sci-fi stuff we see in the movies and gets down to what really matters.
Okay, so here's the key takeaway, the core idea. It all boils down to a three-step dance. Sense, compute, and act. It has absolutely nothing to do with whether it looks like a person. It's all about what it does. It has to sense its environment, think about what to do, and then physically act on the world around it.
So, with that definition in mind, let's do a quick thought experiment. An industrial arm? Yep, it senses parts, and it acts by welding or moving them. A surgical robot? For sure. But what about a software bot, like a chatbot? Well, it senses your text, computes a response, but it never physically acts on the world. See, it can't physically do anything in our world. And that's the absolute key distinction.
And you know, this whole idea is not some brand new thing. The journey really started centuries ago with these amazing, almost magical clockwork figures. Then it evolved into computer-controlled tools in the 40s, and then, boom, the 1960s hit, and we get the first real industrial robots on assembly lines, which have since evolved into the incredible machines building our world today.
Okay, now we're getting to what I think is the single most important concept in all of robotics. This is the secret ingredient, the magic that lets a machine actually achieve a goal when the world is messy and unpredictable.
It's a concept called feedback control. And it's brilliant. Instead of just, closing its eyes and hoping it lands in the right spot, the robot is constantly checking its own work. It's always asking, am I where I need to be? And if the answer is no, it makes a tiny correction, over and over again.
And here's a fantastic way you can explain this in the classroom. An open-loop system is like telling someone to take 3 big steps forward with their eyes closed. They might end up in the right place, but they might not. A closed-loop system, that's one with feedback, is like having a friend guiding you, saying, a little to the left, a little more. It's just way more accurate.
And this loop is what it's all about. You've got the sensor, that's the eyes of the system. It measures what's happening. Then you have the controller, the brain. It compares what's happening to the goal. And finally, the actuator, that's the muscle, like a motor, which takes action to fix the error. This simple loop just runs on repeat, thousands of times every second.
Okay, so having a loop is great, but it's not the whole story. The robot has to be smart about how it makes corrections. Otherwise, you get this herky-jerky motion, like slamming on the gas, then slamming on the brakes, and just rocking back and forth. To get smooth, precise motion, you need something called PID control.
I love this way of thinking about it. Imagine PID control as a committee of 3 experts, all giving their opinion at once. The proportional expert is the impatient one. It sees a big error and shouts, let's go, push hard. The integral expert is the patient one. It notices if you've been off the mark for a while, even by a tiny bit, and makes a slow, steady correction to fix it. And the derivative expert is the cautious one, looking ahead. If it sees the error closing too fast, it says, whoa, slow down, tap the brakes, we're going to overshoot.
And what's so cool is how these 3 opinions work together. Just using P is like having an eager but kind of clumsy helper. Add in I, and that helper becomes much more patient. But when you combine all 3, P, I, and D, you get an expert. It's fast, it's precise, and it's stable. Think about your car's cruise control. It doesn't just floor it and then slam the brakes. It smoothly brings you to the right speed and holds you there perfectly. That is a beautiful PID loop in action.
So, we've nailed down that core control loop. Awesome. Now, let's zoom out and see where that one piece fits into the bigger puzzle, the robot's entire operating system, or what engineers call the robot stack.
You can think of this stack almost like the robot's decision-making process, flowing from the top down. It starts with perception, gathering raw data about the world. That info gets processed, and then the planning layer figures out what to do. And see that control layer? That's where our PID loops live, executing those plans with precision. And it all ends with actuation, the physical movement.
So let's make this real. Imagine a robot needs to pick up a cup. Its perception layer, the camera, sees the cup's location. Its planning software then charts a path for the arm to follow. Finally, the actuation layer, the motors, executes that move, all guided by those PID control loops to make sure it's smooth and accurate. It's that beautiful interplay between seeing, planning, and doing.
All right, so we've got the fundamentals down. Now for the really interesting part. Where does all this technology meet the real world? And what are the big, tough conversations we need to be having about it? Self-driving cars are just the perfect example. Honestly, the control part, turning the wheel, hitting the throttle, that's relatively straightforward. The hard problem is perception. It's trying to understand the world in all its messy glory, dealing with rain, sun glare, faded lane lines, or a kid chasing a ball into the street. That's the real challenge.
And this is such a critical point, especially for educators. It's so important to manage expectations. Because despite all the incredible progress, things that are trivially easy for a 5-year-old, like picking up a squishy grape without crushing it or walking across the rocky beach, are still monumental challenges for our most advanced robots.
Now, this technology also forces us to confront some profound ethical questions. Dr. Sudheendra's material specifically highlights the intense debate around lethal autonomous weapons. We're presenting the arguments here neutrally, just to show you the complexity. On one hand, proponents argue they could reduce risks to human soldiers and react faster. On the other hand, opponents raise grave concerns about losing human judgment and creating an accountability gap. Who's responsible when things go wrong? And that brings us to the final, really challenging question that we have to wrestle with. As we hand over more and more complex decisions to machines, from driving our cars to potentially fighting our wars, figuring out who is ultimately responsible when they fail. Is it the programmer, the manufacturer, the owner? That is quickly becoming one of the most critical challenges of our time.